It's a great honor for me to introduce Hugo Duminil-Copin. And okay, what I can say? I can say that he was rewarded a long sequence of distinctions, and the largest one, prestigious one, is Fields Medal that he got in 22. And it is in mathematics, it is some sort of equivalent of Nobel Prize, but it has a restriction, namely the recipient of this medal have to be younger than 40 in the year of being rewarded, which he satisfies even now. So, so he certainly satisfies this condition. And instead of mentioning all those important distinctions, let me rather say something about some conjectures that do not concern Ising model that he proved. So first of all, this was when it was. I have a piece of paper here with the dates. So when it was published in 12. So there was a long-standing conjecture about a connectivity constant for hexagonal lattice, and there was a particle number, very nice number, square root of 2 plus square root of 2. And in his paper that was, in the best journal in mathematics, we have Annals of Mathematics, there is a short, incredibly beautiful paper that really proves that this is the correct value. It's really beautiful, and I remember after I read it, so next week I organized a seminar in Warwick, and I was somehow lecturing about this proof. And the second thing I would like to mention are two conjectures that are somehow close to my heart. This concerns Potts model. Ising model is Potts model with Q equals 2. So there is a parameter Q, and in 81, before you were born, we were finishing our paper with Senja Schlossman, where we are proving that for Q large, there is a phase transition, discontinuous phase transition. And there was a conjecture by Baxter where he was saying that in dimension 2, the transition should be discontinuous for Q bigger than 4, and it should be continuous for Q smaller or equal than 4, okay? And somehow I was struggling with the problem how to mention this conjecture, because Baxter in his paper was essentially claiming it is a proof. So, and here I am, with Senja Schlossman, two guys from Eastern Europe, who we are to say that this distinguished scientist, Baxter, British, Australian, is wrong. Yeah? So I was, long thinking about, how to phrase it, and at the end I came with the formulation, it seems to have been proven. Okay. And then in the paper, of course, in the theorem, there was a theorem, but somehow in the introduction, actually, to the paper, we were saying that our proof works for a ridiculously large Q, only for ridiculously large Q, and we were not attempting to make an optimization of this Q, how small it is. And in particular, we were not trying to prove Baxter proof. we were shy to call it conjecture. And this is the conjecture that Hugo with his collaborators proved both sides of the conjecture. For Q bigger than 4, it is discontinuous transition, and for Q smaller or equal than 4, it is continuous. Okay, so these are two non-Ising model conjectures I wanted to mention.
Thank you. You know, the presentation of the speaker is always the most stressful part for the speaker. Thank you very much for this very kind introduction. And what is good is that at least you didn't spoil my talk, because that happens regularly, that people want to say something about me and they basically present everything I'm going to say during the talk, sometimes more eloquently than me, which is a little bit problematic. So here, today I really wanted to stick to the Ising model, because this is maybe the most famous model in statistical physics, at least in our part of statistical physics, meaning the one studying phase transitions. And through this example of the Ising model, I want to give you a little bit of a light on what we do in statistical physics, in particular in the math part of statistical physics. And you will see at the very end, I will try to make a connection with what is indeed my, let's say, my real love, which is percolation theory. Okay, so there will be a lot of, this is just to scare people, to check that there are only scientists in the room. You know? No, so I will mention a bunch of names, but don't worry, it's really, I want to sketch some kind of view of the fields. I'm not going to go deep in any of any detail. So one thing we rarely do in a math talk is to justify why we are interested in a problem. So let me start by talking about cooking, right, or French cooking, or in this case it's more a German one, but cooking of a mathematical model. Why do we end up working on a certain model? And again, it's going to be the Ising model to start with. So usually it starts by a phenomenon, like in real life. So here is an experiment. Please do not laugh at it. In particular, I burned myself several times before managing to do it. So then I realized I should preheat my magnet. So it's a magnet, and I'm heating it. And something you may or may not know about magnets when you heat it is that something is going to happen. So do you know what is going to happen after a certain temperature? Sorry? Yes, I was going to say I'm going to burn myself, but yes, it's also the magnet itself loses its magnetization. It's not a magnet anymore, and it falls. Okay? So can we explain this phenomenon using mathematics? That's going to be a little bit the goal of the talk. So it starts by a motivation. Let's now move to the math. So if you want to explain this phenomenon, you are going to make a mathematical model. I like to say caricature, but people say that caricature is not positive enough. I actually like caricatures, as long as they are not mine. That's fine. So a mathematical caricature of what a magnet is. And we are going to make a few assumptions, like in every caricature. So the first thing is that we are going to think that our magnet is made of a huge collection of tiny magnets. Okay? I will call them spins because I'm used to call them spins, and if I don't call them spins, I will still do it once out of two. So let me call them spins. So they are like tiny, tiny magnets. And these tiny magnets, if I just make this assumption, it's going to be very difficult to work on the model. So I'm going to make further assumptions on the behavior of these magnets. The first one, and I think many mathematicians will be unhappy about it, and many others, so half of the room is going to be happy, half the room will be unhappy. I'm going to simplify by discretizing. So there are two types of mathematicians. People who think that discretizing is making things harder, people that think that discretizing is making things simpler, right? I'm actually in both parts. It depends on the case, but in this case, it will make things simpler. So let's discretize and assume that our small spins, they are in fact regularly spaced on a lattice. I'm going to take Z2 or ZD. I could take another lattice. In fact, I could even take things that are not really lattices, but if I take a lattice, I have translation invariance, and this is going to simplify a lot everything I will say later. So I imagine that it is on a regularly spaced, on a square lattice, on the paving of your kitchen for, I mean, if you have squares, if you have hexagons, then too bad. And I'm going to take a finite portion of this lattice. It's an infinite lattice. I take a finite portion. and I imagine that my small spins are located on the nodes, on the vertices, we say, of this lattice. That's the first assumption. This one is not a big one. In fact, it's actually not so far from reality. Of course, in a material, the atoms are not regularly spaced, but they are homogeneous in space. So it's not a very big assumption at the end. Let's make another assumption, which is much worse. We are going to make the assumption that these spins, these small magnets, they can be oriented only in two possible directions, north or south. This, a priori, is very strange, right? I mean, you would definitely expect them to be orientable in any direction in space. We can go back to this when it will be your turn to ask me questions. But in this case, I'm going to look at this very anisotropic, if you want, magnet where the small spins point in one out of two directions. So one out of two directions in math, we are just going to say +1 or -1 for each one of these guys, right? +1 if it's north, -1 if it's south. So a magnet is what? It's just a function that for every side of my portion of the lattice is telling me if the spin on this side is pointing north or south. So it's a function from the vertices of my graph into +-1. Okay, you know what is my mathematical magnet now. Okay, what do we do now? Well, we want to measure something on this magnet. We want to measure its strength, right? How much it's attracting things. And a good way of measuring that is simply to make the average of the spins. Why? Because if all the spins are pointing north, you feel like they are going to clearly pull any other magnet that I would pull nearby in one direction. So I would get a magnetization +1, for instance, or -1, which would give me a strong magnet. On the other hand, if the magnets are like half of them are pointing north, half of them are pointing south, then clearly already within the magnet, they are canceling their strength in some sense, and the magnet as a whole is going to have no attraction power. Okay? So in this case, the magnetization would be near zero, and that would indeed kind of measure, we can believe that it's going to measure the strength of my magnet. Okay? So I have a magnet, I have an observable, what we call a measurement, if you want, on my magnet. Now, magnets are really made of a huge collection of these things. Think that this should be basically the magnetic like moments of the atoms, or even the electrons in atoms. So you should have like even more than number of atoms in my magnet. So it's a huge, huge collection. So in this case, when you have a very complex system, here it's going to be the case of magnet. It will be the case of basically anything. It can be a population for the COVID. It can be whatever you want, like the atoms in the air in this room. We use randomness. Right? Randomness is not going to complicate things. It's going to, on the contrary, allow us to focus on the typical behavior instead of having to consider all possible behaviors. So randomness is a simplifying feature here, like always, almost. So we are going to use randomness. We are going to choose a magnet at random. And in nature, things are more likely if they have a smaller energy. So let's first, in order to define how we sample at random this magnet, let's first discuss what is the natural kind of energy I could put on this magnet. Okay? So, wow, things moved more than I was believing it would. Okay, anyway. So what we are going to do is a very simple assumption, is that if I look at a magnet, a small spin, it kind of wants to be aligned with actually all the magnets, the spins around. Like every big magnet, the small magnets wants to align. But what we are going to do, and this is an assumption, we are going to assume that the leading order of this energy is actually due to nearest interaction. Of course, it should decay with the distance, the interaction. So let's just make the very strong assumption that two neighboring spins interact, the others do not. And then you want to align, so you can say that there is an energy cost for any pair of spins, which will be -1 if they agree, and +1 if they disagree. This is an arbitrary choice, but I could put -A plus B if I want. Then by shifting the energy and by a constant and then rescaling, I would just get back to the +-1 case. So this is not a big assumption. But what is really big as an assumption is, again, that I'm only looking at nearest interaction. These two guys, I'm not looking whether they agree or not in terms of computing the energy. Once I have the energy, I go back to Boltzmann, and I say, well, then the probability of a given magnet is going to be proportional to exponential of -1 over the temperature times the energy. Right? So the higher the energy, the smaller this term, so the smaller the probability. This is just a constant because, you need to renormalize to have a probability measure. At the beginning, I was not putting it. Then probabilists said that I would be banned from coming to their university if I keep doing that. So now I renormalize, okay? So this is a probability measure. If I sum over every sigma, I get 1. And notice that this parameter t, I didn't use it before. I introduced it here. I call it the energy because it's the temperature because it's kind of the level of excitation of my system. How much, you want to minimize the energy. You are a very nice audience. So you are all pointing towards me. Okay? Now imagining an audience like, I don't know, the same audience but with 10-year-old. There's good chance that they will be a little bit less following the rule. So some of them will be actually talking to the person behind them just out of, they know that it's going to increase the energy of the room, but it's just that there is a little bit of excitation in the room, okay? And it will actually increase when time passes. Yeah, it's an experience that I already did. It was painful. Not with this talk. I'm not giving this talk to 10-year-old, don't worry. But anyway, I didn't want to give you the same talk I give to 10-year-old. That would have been... okay, so the T is telling you how much you take into account this excitation. The higher the T, the smaller 1 over T, and therefore the more uniform, the closer to 0 this is, and therefore the more uniform the sampling of sigma, the less you care about the energy. On the contrary, if T tends to 0, meaning you have lower and lower excitation, then 1 over T becomes larger and larger. So this is going to do what at the end? It's going to force, when T is equal to 0, this measure is what? It's going to be a Dirac measure, or at least a sum of 2 Diracs, an average of 2 Diracs, because it's going to try to minimize the energy. Look at what we call the ground states. And there are 2 ground states, everybody up, everybody down. So it's going to be 1/2 on these 2 magnets, not the most interesting system. Okay? Okay, so there is now a temperature. That's good because that was also appearing in my experiment. I wanted to see how the behavior of magnet evolves when I move the temperature. Okay. Before, I had a given magnet, and I was looking at its magnetization, this average. So now that I have a random magnet, I can look at the average, again, so this is the measure, the average of the magnetization. And I get 0. Why? Simply because a magnet and its full, indeed, symmetric version where I flip all the spins, well, by definition of the energy, they have exactly the same energy, so they have the same probability, but they have opposite magnetization. So here, I'm getting something a little bit disappointing because whatever the temperature, I get 0 magnetization. Yeah. End of the talk. Let's go for a beer. Well, let's hope that you will be less disappointed at the end. It's a kind of joke that can backfire because if you don't like the rest of the talk. Anyway, so here there was something that we didn't do, is that we didn't take into account the fact that our magnet, it lives in an environment. And this environment, it's going to break the symmetry between this flip symmetry that I have is basically not so natural. So let's try to implement this this breaking of symmetry, and I'm going to do it in a way that Baxter would not have liked at all, or any physicist would not have liked. I know it's not the right way, but for the talk, it's much simpler, and it ends up giving you exactly the same result. So I want to implement the existence of an external magnetic field in some sense. For instance, the Earth's magnetic field for any magnet in the... So what I'm going to do is I'm going to force the spins on the boundary of my magnet to be all in one orientation. This is not so natural. I mean, what would be natural is that the external magnetic field is kind of tilting a little bit. It's favoring for every spin in my magnet, favoring a little bit pointing in the direction of the magnetic field. I mean, the magnetic field doesn't see the materiality of the magnet. There is not like boundary or not. But again, it's simpler to present it like that. Don't worry about this red dot. It's just an experiment. One day I will tell you why. But sorry? Yeah, it came from no. That's true. That's how you sample this. But no, the experiment is that I'm comparing you to your cats, right? There is a red dot moving, and I'm trying to check whether you are. Okay, and what I do is I take this, so basically I'm forcing spins on the boundary to be +1, and I'm just taking the same measure. So it's exactly the same measure as before, it's just conditioned if you want, it's forcing spins on the boundary to be +1. And if you think about it now, flipping the spins is not so easy anymore because you cannot flip the spins on the boundary, they are forced to be +1. So you can only flip the spins inside, but if you do it, of course, all the mutual interactions, the energy coming from the mutual interaction will not change, but the one between boundary side spins and the guys inside, they will flip, they will change. So there is no flip symmetry anymore, and what you can actually prove is that the magnetization in this case, when you average against this measure now, the one conditioned, is strictly positive, always. So I didn't solve my problem. I came from, it's always 0, so it doesn't seem to be explaining my model, to it's strictly positive, which is also not explaining my model, my experiment. It's going to be a long hour for you, don't worry. But it's because I mean, this is indeed, I mean, if I take a box like that, I don't know, it's like a 10 by 10 box. Indeed, it will always be strictly positive. But my magnet is definitely having more than 100 small spins. It's having a huge number of spins. So I mean, huge for a mathematician basically means infinity. So let's look at an infinite system. Let's look at what happens when the box gets to ZD. I take bigger and bigger box, and I end up with a quantity on ZD. So this quantity that depends on the box, it gives me a sequence, and it's going to converge. In fact, it's going to decay when you take bigger and bigger boxes to a certain quantity. And this quantity, I'm going to call it the spontaneous magnetization. But now, okay, even if this is strictly positive, you agree that the limit itself can be 0 or strictly positive. I have no clue what it is. And this is the one that is going to give me the information on the behavior of my magnet. It's actually giving me a lot of information because these measures, when you take the limit of this probability measure, so you understand why I did it on a finite box, because the energy was a sum of ±1. If I'm directly in infinite volume, it's an infinite sum of ±1. Mathematicians do not like so much these kind of things. So that's why I was defining it in a finite volume and then take the limit. But I can take this limit. I get a way of sampling an infinite magnet, if you want. And the good way with this, the good thing with this measure is that's what we call an ergodic measure. So in particular, it's telling me something interesting, is that this is an average. So a priori, you could answer, yeah, but I mean, how do I get an information on every single magnet? If I meet a magnet in real life, it's one realization of this random magnet. It's not random itself. Well, it is due to quantum physics, but it's not random itself in my way of describing it. But ergodicity will tell me that, in fact, its magnetization will be almost surely the average magnetization. So this average magnetization is actually giving me information on the typical behavior of my realizations of this random magnet. Okay? So the question now, you understood the model. So the question is, what do we do on that? And in particular, can we prove there is a phase transition? In the sense, can we prove that depending on the temperature, I may get 0 for the spontaneous magnetization, or strictly positive for the spontaneous magnetization? Strictly positive will correspond to the phase where I have an actual magnet in real life, and 0 would be the phase of what we call paramagnets, which are things that are not magnetized if there is not a magnetic field around. So this is in some sense the summary in a diagram of what we want to prove. I started around here with my magnet at normal temperature. I hit it, and at some point, I cross a temperature, and I start to have 0 magnetization. I'm not magnetized anymore. Can I prove that? Okay. Okay. This critical temperature, by the way, it's called Curie temperature. So it's Curie not for Marie Curie, but Pierre Curie for once. This is rare. And also, as usual, it's called Curie temperature, but he was not the person who discovered it. And you know the worst thing is that I always forget the name of the French guy who discovered it, which is really bad because I'm actually contributing to this cancellation. Anyway. Okay, so I think it's the right time to tell you a little bit about the history of the model, because in some sense it's a little bit typical from history of physical models, and it's quite interesting. So the model is called Ising model. It was not invented by Ising, again. This one I know the name of the person who invented it. It's Bures. And Ising was his PhD student, and in 1925, he did what today is probably a very simple exercise. But I mean, let's also remember that, computing things with Newton's law is also a very simple exercise. It doesn't diminish the discovery of the thing at the time. You should not evaluate the difficulty of something by modern standards. But it's true that it's an easy exercise still. So he proved that when you look at a one-dimensional magnet, in fact, this critical temperature is 0. Meaning as soon as you are with positive temperature, you get 0 magnetization. So there is no one-dimensional magnet. And at the time, the thing is relatively easy. Actually, you have many ways of doing it, but you can, for instance, try to compute it almost by induction, like on the size of your magnet. I mean, you have different ways of doing it. It's not very difficult. But the one-dimensionality is very important for the computation. So what Ising did is to try to cook up. I mean, of course, Ising knew that a magnet is not a one-dimensional object. So he tried to cook up a 3-dimensional object out of this by doing some, patching some things that are 2-dimensional through one edge to try to create the 3rd dimensionality. There he was still able to compute things, and he was also getting 0. So he said, well, conjecture. This one was a conjecture. TC is always 0. The model is just not explaining anything about magnetism. It's always 0. And that was not a good news, right? Because in some sense, it was saying that the reason why they introduced this model was unfortunately not working. So he said, I discussed the result of my paper with Professor Lenz and Paoli. There was some disappointment, I love this quote, some disappointment that the linear model did not show the expected ferromagnetic properties. So by some disappointment, Ernst Ising meant that he just quit research just after because it was so disappointing. So well, he he left research and actually didn't know for a very long time that, I mean, Ising is one of the most cited names in physics. And he learned about it only like 30 years later, basically.
47.
Sorry?
47.
47?
In the year 47.
So 22 years later. Okay, I'm from Paris, not Marseille, which is also France, but I always exaggerate a little bit still. So, so anyway, 22 years later. So that was very bad. That was a coin. And another very bad thing about this model, and that probably, if there are physicists in the room, was the first thing that struck you, is that the model is clearly a catastrophic description of ferromagnetism for a very simple reason, is that ferromagnetism is actually a quantum phenomenon, and this model is purely classical. There is nothing quantum in it. And at the same time, in 1928, Heisenberg introduced a model which is using quantum physics to describe the thing. Okay? So, only 3 years later. So that was like two very bad reasons for keep working on this. But, I mean, you can guess that if I'm here, there are also some good things about this model, some good things. And these things actually happen two things happen from the same man, basically, Rudolf Bures, which in 1936 proved two things. First thing, he proved that Ising was totally wrong. But when I mean totally wrong, it's really, really totally wrong. So it's always strictly positive if it's not one-dimensional. So dimension 2, 3, 4, Bures proved always strictly positive the critical temperature. So there is a phase transition. Of course, trying to make people wrong is still, I mean, you never admit it, but it's kind of very fun, right? So for instance, we try to make him even more wrong, Ising. We are still a little bit failing, but clearly, I would say that in the 10 next years, we will find somebody smart enough that will prove it. So of course, here it's for lattices. So the dimension is an integer. But you could actually cook up models, graphs that are not lattices. For instance, graph with isoperimetric inequality with a dimension d, which is not an integer. Whereas the prediction is that 1.000000001, TC is positive. It's really like only the linear chain is failing. Anything else, you get positive critical temperature. And Bures observed the second thing. Okay, because this is only answering the worry of Ising, not so much the worry that it's not classical, that's a classical model. But what he observed is that at the time, there were modelization of other physical systems. For instance, binary alloys, so mixture of two types of atoms, or more generally, cooperative phenomena. Because here you feel, right, for instance, if you think that you have a population with two opinions, A and B, and that you are a little bit sensitive to your neighbors, you want to agree with your neighbors, then in some sense you feel like, I see somebody doing like, no way, I want to disagree with my neighbors. That also happened quite a lot. But this model, the models that people were cooking up for describing these two systems, they were in fact just the Ising model, again. And if you have followed a little bit the news, last year the Nobel Prize in Physics was given to people that developed the first models of AI, and they were basing their argument on an Ising model. An Ising model where you don't necessarily want to agree with your neighbors. So an Ising model where you have a tendency to agree with your neighbors, and this tendency can be negative. You can also hate your neighbor, right? And that happens quite a lot as well. So that would just be that in my sum of minus sigma x, sigma y, I could add sum of minus jxy, sigma x, sigma y, where jxy is a constant. And this constant could be negative, for instance, for some vertices or not. And in fact, you can train systems where you are going to try to tune the jxy in such a way that your system will be able to spit out observable that mimic I don't know, recognition, facial recognition, blah, 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 blah. And so that was, in particular, the work of Hopkins and the people that got this Nobel Prize. This is not what is used nowadays for the most efficient AI systems, but it was one of the first attempts of that. So here you see the Ising model, by failing describing accurately one phenomenon, in some sense it succeeded in another thing, which was to be a model that is fairly universal, that you can apply to different systems. And this is something that is very important in modeling in real life, in science, is that you don't necessarily want the most efficient model, because this model may be too precise, too narrow. The higher altitude you stand, you will definitely see things from farther away, so it will be less precise what you will say on every silicon system, but you may appear to be high enough to see that certain things are, in fact, the same from this perspective. Okay, so there is a trade-off, and it's really something important to justify, in particular, why statistical physics is so interesting, and why models are interesting. So the discovery of Rudolf Peirce, the two discoveries, they kind of allowed to make the Ising model survive a little bit. But what truly brought fame, I would say, to this thing, to the Ising model, is a beautiful result by Lars Onsager. He was a theoretical chemist. So, I mean, I have to say that, it's contradictory. I mean, contractually, I have to say that, but at the time, many of these theoretical chemists were in fact mathematicians. Just you should not tell them. I mean, they would really dislike it. So Lars Onsager was a theoretical chemist, but also a brilliant mathematician. And what he did is the following. So on Z2, so the two-dimensional system, he computed, this is the formula, he computed the free energy of the system. So what's the free energy? It's another observable of the system. I told you that by ergodicity, all magnets will, all this realization of this random magnets, almost surely they will have a certain magnetization, this m star of t. But you could also ask another question, it's what's their typical energy? So of course it's an infinite system, so the energy is not really, but you could look at the energy per unit of volume, and you get the free energy. So he computed this quantity. And just to go back to, and by the way, so he computed it in a very complicated way. It's actually not so easy to even write a modern proof that is understandable of this. It's possible, but it's difficult. Bruriah Kaufman, who was his postdoc, did simplify quite a lot the thing. It was still a little bit complicated. But nowadays, there are many, many different approaches proving this. In fact, there is even a paper that is called the 399th solution of the Ising model. And we didn't discuss prior to this talk, but the Baxter is the same Baxter. And this is actually a proof in this paper. So I have now to correct. I agree with you that I will not call the other one a proof. But this one is a proof. So, I mean, 399th is a little bit of an exaggeration, but basically there are like at least 20 different proofs of this statement, some involving only combinatorics, some involving algebra, analysis. It's actually beautiful graph theory. Basically, whatever your favorite domain, well, maybe I should not say that, but you can try to prove this result. Okay, just to get back to the quantity I defined, you can also look at the spontaneous magnetization. And there you can compute, the formula is actually simpler, it gives you that. And when you see that, you realize that you even get, so this is a plus, the positive part of this quantity, so you get actually what is the critical parameter. This is strictly positive below 2 over log 1 plus square root 2, and it's 0 above. The person who proved that, it's actually a refinement of this argument, it's quite complicated, was a young mathematical physicist or physicist, theoretical physicist, Chen-Ning Yang. And this is a Young that many mathematicians and theoretical physicists will know. It's a Young from Young-Mills, from Lee Young, from Young-Baxter. It was one of the most important theoretical physicists of the 20th century. And he describes this computation as one of the most difficult computations he had to do in his life. But you have an explicit computation. So you know the critical parameter, and also, and this is one of the reasons why this body of work is very, very, very important, also you have the behavior when T tends to Tc. When T approaches the critical temperature, so when this quantity gets close to 0, so this is going to behave like T minus Tc. So this is going to behave like T minus Tc to the power 1/8. So you see, that you understand what is the behavior of the magnetization when you approach the critical temperature. And these are questions that are very difficult and very important. You want to understand this, what we call this exponent, this 1/8. And before this body of work, essentially, I'm exaggerating a little bit, but essentially there was no result that was able to compute this kind of critical exponents, except for results that were assuming that the system is what we call mean field, meaning that you forget entirely about the geometry of your system. You just think every atom is interacting with any other atom in my system in the same way. You forget entirely about that, and there things become much simpler because in some sense they reduce to very simple equations. Except that this assumption, this mean field approximation, which is used quite often in many systems, it's kind of an infinite dimensional approximation. It doesn't give you 1/8, it gives you 1/2 when you approach the critical parameter. So here, it was the first time, essentially, where you were getting a non-mean field exponent rigorously. Even more interesting, they managed to do it on the triangular lattice, on the hexagonal lattice. When you do that, the critical temperature is not 2/log1 plus square root 2. I don't know, I think one is 1/square root 3 or something like that. The temperature does change, the critical temperature. And this is actually very reminiscent of what happens with real-life magnets. If you take a magnet made of iron, pure iron, you need like, I don't know, it's 780 degrees, the critical temperature, something like that. You can guess that this is not what I reach with my with my light. I did ask for the big thing to the physicists in my university, but they said that they would never leave that to a mathematician. So I had to, so what was my solution to make the experiment? I just looked for another material, and you have this material where the temperature is way below. It's a few hundred, like 200 or 300, and that actually is what you reach by heating with light. So the temperature does change depending on the material. Here, the temperature, the critical temperature does change depending on the lattice. But what did they discover? Is that when the temperature gets close to the critical temperature, the behavior is always T minus Tc to the power 1/8. You get the same 1/8. It's called a universal property. And these computations, they participated to the realization that there should be a universal behavior in models of statistical physics. And this universal behavior is a little bit why this kind of work is not totally useless. Because if, of course, the delicate description, like choosing the square lattice, is changing totally what happens in your system. If you choose a triangular lattice, you get something completely different. You would agree with me that then I'm absolutely not going to manage anytime soon to describe something on a real-life magnet. It's too sensitive to my discretization. But if indeed there are properties that do not depend too much on this discretization, then I can hope that these properties are shared in such a universal way that they would also be the properties of an actual physical system. And there are physical systems that have the exponent 1/8 ruling their behavior, like the Ising model. Okay, but all of that the mathematical study, like how you derive this 1/8, relies on a very specific property. So it's really on the square lattice, on the triangular lattice, on any strictly planar lattice. It's based on what we call integrability. And for instance, if I ask now, I told you I'm doing the nearest neighbor interaction. But imagine that, of course, this is an approximation. Imagine that I tell you, this guy is also interacting with this one. This one is interacting with this one. Something that if you draw an edge between them just to materialize the fact that you are interacting, then the graph is non-planar anymore. You cannot draw it in a planar fashion. As soon as this happens, even if you say that it interacts very, very little, that the interaction is plus minus epsilon, not plus minus 1, as soon as you do that, integrability breaks down. But universality is kind of telling you, come on, it should be the same system. This should not change much. You should still get the 1/8. But the proof itself completely breaks down. So it's a very powerful technique, this integrability, but it's very delicate. Okay, I told you that this breaks down even if you do really next to nearest neighbor interaction in 2D. So imagine what happens. So this is, by the way, the drawings that's what you see for the drawings of Curie, of Pierre Curie. If you draw the magnetization, it looks like that. There is a singularity here, but it's a continuous one. So the function is continuous. So I told you this you get from integrability, this part. But what happens in a 3D model? In a 3D, I mean, you want to look at a 3D magnet. So if it already breaks down when you look at next to nearest interaction in 2D, you guess that this is never going to work in 3D. By the way, some people try to prove that the 3D Ising model is integrable. I would not recommend that as a career choice, because I don't really see why it should be true. And I think that all attempts, I mean, I'm certain all attempts have really failed up to now. So the 3D model is not integrable, so you cannot compute things. So you're a little bit in the situation, I don't know if you know this very classical theorem of probability. It's called the central limit theorem. It's the things, for instance, when you toss coins, you know that half of them roughly are going to be tail, half of them is going to be face. And when you look at the error that you are making, like it's not going to be exactly half, right? The error you are making, it's a random Gaussian random variable, blah, blah. At the very beginning, how people did come up with that? They started by cases where when you add these like random variables, you get something that you can compute. For instance, if you add 0, 1 random variables, Bernoulli random variable, you get a binomial, and there you can compute explicitly the asymptotic of the behavior of the probabilities. Here it's a little bit the same. In 2D, you can compute explicitly things. But very quickly, you are bound. I mean, there are only few cases where you can compute explicitly, so you need to go beyond and try to cook up techniques that do not rely on exact computations. And here, to treat the 3D case, you will have to do that. So that's when I start coming in. Because I don't remember exactly when it was, but in 2010, I will tell you exactly on which problem I was working, but later I will tell you that. But I realized that the equivalent of this problem for the Ising model was not known, and that struck me as something very strange. Meaning that the first question you want, so we know by Bures, 1936, we know there is a phase transition in 3D, okay? And phase transitions in nature, they come in two kinds. The discontinuous and the continuous ones. The discontinuous, you know one, you cool up water at 0 degrees, it becomes ice, right? It's discontinuous because that's one of the fun things you can do at home with your kids. The volume actually blow up by a factor, it adds 10 or 20%, and that makes the bottle explode if you do things fun. Right? Actually, at 100 degrees, it's even more violent. You get a factor 10,000 when it becomes vapor, and it's actually why you have motors that can work with vapor. So these are discontinuous phase transitions. For the Ising model, it's a continuous phase transition, as you can see here in your system. So there is a phase transition. Here it's ferromagnet, here it's paramagnet, but it's a continuous one in the sense that the order parameters, what you are measuring, move continuously. That you see in 2D by the exact computation, but this is a measure on magnets that are 3D, and question, is the phase transition of the Ising model continuous in 3D? And we were in 2010, and in fact, nobody knew how to do that. So what I want to explain to you in the last minus 10 minutes, no, I don't exactly know how long, no, I think I still have a little bit of time, but I want to tell you how you can prove this. I'm not going to give you the full proof. I could see people a little bit panicking. But I want to tell you a little bit about a fun story about this. Fun for a mathematician. So indeed, for the Ising model, the phase transition is continuous. We proved that with Michael Eisenman and Vladas Sidoravicius. And in fact, the only thing you need to prove is that at the critical point, exactly at the critical point, the spontaneous magnetization is 0. In some sense, you know that it's going to decay to a certain value. And if this value is strictly positive, then it drops to 0. But if this value is 0, then you have something continuous. So let's try to prove this. So it's good. It's what you see in real-life magnets. In order to do it, let me start by saying that what you are going to want to understand is the behavior, how much your spins correlate, how much the fact that one of the spins is pointing in one direction is impacting the behavior of another spin, in particular when they are far away from each other. So let's introduce for that what we call the spin-spin correlation. So it's just the average of the spin at 0 and the spin at x. So this is exactly going to measure how much the spins wants to be aligned. If they were totally independent, you would get probably 0, right? Okay, so let's try to look at this. This is just a definition, but you can ignore it. And notice the first thing. If I take spins that are farther and farther away, you do expect that it's going to be more and more independent, right? If they become totally independent, in fact, each one of them will have a certain average. And if you look at the measure with plus boundary conditions, the one where you broke the symmetry, it's pretty natural to guess what is this average for one spin. Because remember, the magnetization was the average in space. But the average in space, if the measure, for instance, is translation invariant, is nothing else than the average at one point. The same thing. So the average at one point is the spontaneous magnetization. So when I let one of the points go to infinity, the correlation should get to the thing that I would get if they were independent, meaning the average squared. Okay? But there is another result, which is a little bit too complicated to get, but which is saying basically that there is a quantity that is continuous from the right when you decrease the temperature. And this quantity, so it's a limit when x tends to infinity of the measure of the correlation sigma 0, sigma x. At the critical temperature, then, it should be what you would get for strictly positive temperatures that are strictly above Tc. So you should get 0. That is harder to justify, but it's something that is, I like to call it old, but I realize that some people are going to be a little bit upset at me. But it's older than me. So older than me is old. So it's from the 80s. Sorry, Roman. But so you get 0. So that looks very, very good. I mean, that means at Tc I get 0. This I get spontaneous magnetization. So spontaneous magnetization at Tc is 0. And you are wondering why I'm here, right? Because that doesn't seem like a very difficult theorem. Anyway, I don't know how to prove difficult theorems. So the proof is actually not that difficult, but of course it's a little bit more difficult than that. Why? Because here there is a plus and here there is no plus. And in math, we know that when there is a sign which is not the same in two formulas, there are two possibilities. Either it's very deep or it's a typo. All right? I'm not saying which one is the most likely, depends on the people, but in my case, the most likely would be the typo, but in this case, it's not a typo. These two measures, they are a priori different, even when you put TC here. And actually wondering whether they are equal or not is the whole difficulty. If you have a discontinuous phase transition in nature, you have different state of matter exactly at the critical point. When you cool up water at 0 temperature, you are going to have, at some point, a coexistence of water and ice, right? It's not that it's going to immediately turn into ice. So here, I need to prove that there is a unique state of matter at Tc, meaning that I need to prove that mu Tc plus is mu Tc. If I do that, then the arrow is fine. Okay? So the difficulty is to prove that what we call the free boundary condition, when you don't break the symmetry, is the same as the plus boundary condition. So that's where I reach what we call in French the trou normand. So the trou normand is what happens when you have already eaten way too much and you want to eat even more, which is a natural thing in France. So you take this very strong alcohol, you drink it, it dilutes everything in your body, and you can go for a second dinner. So that's a polite way to say that this is half the talk. No, I'm going to stop before the end of the talk, but the trou normand is going to tell you a little bit about another model, which is called percolation theory. So percolation theory is a totally different model. It's a model for porous medium. And I'm going to model this as a random maze, if you want, as a random graph, by saying that in my Z2 or ZD graph, certain edges are small pipes that let water go through, and certain edges are just not crossed by water. So the red edges are crossed by water, the gray are not. And for instance, what you can do is you can say this edge is open with probability P, so it's a pipe with probability P, and it's closed with probability 1 minus P. It's like you toss a biased coin for each one of the edges. You end up with what we call Bernoulli percolation. And if you do that, then you can look at the connectivity properties. You know, if I pump water here, where does it go? So there it will go nowhere. If I pump water here, where does it go? Then it can go anywhere there. And let me color the connected components of this random graph in different colors. And here are two simulations. This is for P equals 0.495, I think, something like that. So 495, so very, very close to 0.5, but from below. And you see that all the connected components are tiny. So this will model a model which is not at all porous, a material that is not porous. Here, it's not an anomaly of the simulation. It's 0.505, so just above PC, 0.5, sorry. And oopsie. And there you see a huge connected component of red, meaning if I pump water here, it will manage to go up to there. This will be a porous material. And there is a phase transition, again, a change of behavior at 0.5. Okay? So this is percolation theory. It has nothing to do a priori with magnetization. Okay? So what is the connection with magnetization? Oh, by the way, so as I said, it's meant to model porous material. And interestingly, so it was invented by mathematicians around 57, something like that. But there were very interesting work, in particular by Rosalind Franklin, the same one as for DNA, that was actually doing experiment on coal, depending on the size and the size of the atoms and the in the gas and the temperature, to try to see whether it was porous or not, to try to build. For instance, I mean, in her case, it was not trying to build a mask, but trying to measure, in some sense, the density of coal. And this was during the Second World War, so it was 20 years or 10 years before, 15 years before the actual invention of percolation. So the first percolation experiment, but way before. So what's the connection with our case? And I'm going to finish on that because I can start seeing people sweating a little bit that I'm never going to finish. Is that, in fact, when I look at my correlation in the Ising model, how much the spins correlate, it is naturally connected to a percolation model, in the sense that I can rewrite the correlations in terms of a percolation model where it will be the probability for this percolation model. If I look at the correlation between the spins at 0 and x, the probability that 0 is connected to x. It's like you are encoding the correlations in your system by a kind of random path, by a graphical representation. So, of course, you can guess this percolation model is not going to be sampling edges independently at random. This will be too easy. It's much more delicate and complicated way of sampling the edges. In particular, exactly like if I tell you that a spin is +1, it's going to increase the probability that the neighbors are +1. Here, the fact that an edge is open, it's going to increase the probability that the neighboring edge are open, for instance. But there is a percolation model, a complicated one, but there is one. And you can write this, so there is a dictionary between the percolation word and the Ising word. And when you have a dictionary, very often it's a dictionary that contains more than one word. So there are more than one identity thanks to this dictionary. You can, for instance, look at the difference between the spin-spin correlation with plus and the spin-spin correlation with free boundary conditions. And you get the probabilities that 0 and x are connected to infinity in my percolation model. But now comes, I'm going to ask you to remember the previous slide. It's difficult, but there was a huge red area, right? So in the case where we were above 0.5, in fact, what happened is that there was a huge and unique infinite connected component, in fact. I cannot draw infinite systems, but if I would have, this red area would have gone to infinity. And the important thing is that it's unique. So if it's unique here, 0 and x are connected to infinity, what do I guess? What do I deduce? That 0 and x must be connected together. There is no choice. Of course, you need to prove this uniqueness, but in this case, you can do it. So because of the uniqueness, here 0 and x are connected together. They are also connected to infinity, but together also. But if they are connected together, if I plug this thing here, it means that this quantity is smaller than this one. So in particular, the plus is smaller than twice the 3. I didn't prove they are equal, but I proved it's smaller than twice the 3. But this is going to 0. That's what I was saying. This is going to spontaneous magnetization squared. So it's 0. Voila. It's easy, right? Math is easy. Of course, I lied to you, but I'm allowed to do that, right? It's for your own good. Like every good father, I know when... But it's really, this is the moral of the story, is that a very difficult question on the Ising side becomes, in fact, a fairly simple question on the percolation side. And all this connection that we are so much used to do in math, we are always playing this game, right? We are making analogies between different fields of mathematics and trying to find then on which side the question is the easiest to answer. And here, it's a typical thing with Ising and percolation. We create a link between the two. By the way, this link was not due to me. It was there for a very long time. And then you get to the right side of the translator, and you prove the thing. Thank you very much for your attention.
Questions?
I have never thought about it, actually, and it would probably not make sense to try to manage them or to manufacture them. But if I understand Ising model right and the results from it, it would be really hard to make magnets which try to mimic a line segment with their magnetizations perpendicular to the line, since they would be pretty unstable with their magnetism. Is that right?
Yeah, I mean, so there are, to the best of my knowledge, I think I can talk here, right? I was told, is it fine? Yes. Yes, okay. Indeed, I don't think you can manufacture this kind of thing. So when you, this is something that can come up later on in questions, but I want to bounce on the mention of the POTS model that was made at the beginning. You could assume, for instance, that there are more than 2 states, and then there are some crystalline behavior where I think for the 4-state POTS model, I think there are some systems that have like 4 orientations. For Ising itself, I don't think there are. But for instance, and this is where universality is kind of mesmerizing, when you look at 3D Ising model at the critical point, it's still predicted by many physicists that the critical exponents are at least very close, maybe even equal, to what you get at the 3 critical point of water. So there is a point of pressure and temperature where you end up at what we call a 3 critical point. So there are real-life systems related to Ising. I don't think there are 3D magnets that manage to be so anisotropic that Ising is a good description for them. But I'm not a specialist, so I may be wrong on that. And I prefer to be on the conservative side, which is for a mathematician always to say that you are useless, right? So I don't think there is any real-life application of what I do. But yeah, I think they are hard to manufacture.
There was a paper in '68 where they were comparing, somehow creating the experiment for any Ising model you can imagine. 1 dimension, 2 dimensions.
Okay. Now that you said that, it reminds me that in a very low temperature experiment, which is this new thing that, I don't know, 10, 20 years that they managed to cool down systems so much that they can then have a few atoms and try to, there they managed to manufacture a system that behaves like Ising. But it's handmade. It's very funny because there it's like the experiments try to cook up a system that behaves like Ising.
Maybe I want to ask, so you were earlier telling that for this, you have this critical exponent of 1/8, which can be proved when things are integrable, and you were also telling us that once you start to do next nearest neighbor, you're not integrable. But are there cases in 2D where you can still prove the 1/8 exponent, even though you're not nearest neighbor and not integrable?
So there are some cases which there is this big, one of the reasons why you believe in universality in physics is that you have what we call the renormalization group in physics, which is that you can iterate, in some sense by scaling down, like by looking from farther and farther away to a system, you can think of every iteration of looking farther and farther away, like rephrasing, like having a certain model, you rescale, you get a new model in some sense, and you rescale again, etc. And by rescaling up to infinity, you should end up, like in every dynamical system, with a fixed point of this renormalization picture. And this observation is beautiful because if you believe there is a unique fixed point, then any system when you rescale, any reasonable system when you rescale, you should end up with this fixed point. That's why you believe in universality. In math, we have a few examples, I was told, of dynamical systems that have more than one fixed point. So it's very difficult to justify this argument. But it happens that for the Ising model, there is a regime where we manage to run this multi-scale analysis to study a system that is close to another one for which you know the result. So let's say you square lattice, you know you will get 1/8. So take a model which is close to the square lattice. If you have this vision of renormalization group, you are thinking, maybe I'm starting close to the point, maybe I get to the same fixed point at the end. And it happens to be doable, so there are work by Giuliani, Mastropietro, Greenblatt, etc., that do that for the Ising model. So you do square lattice, nearest neighbor, and you add very weak non-nearest neighbor interaction. So they don't get the 1/8 yet, but they get certain exponents which are called energy exponents. This one they get. So for instance, they would manage to prove, they did manage to prove, that the free energy has the same behavior when you approach the critical point. So some things are known, but in a perturbative regime.
Thank you for a nice talk. My question is concerning not exactly about Ising model, but something very related. It's more related to, actually it's not the POTS model, as you've been mentioned, the POTS model in the beginning of the talk, but it's the magnetized Ising model. So instead of energy being the product of the spins, you add also a sum of the spins. And I believe that it's unknown yet the proper formula for the free energy, right?
Yeah, so these systems are much more difficult to study. For instance, the percolation translation is a nightmare.
I was also struggling with this problem for many months, and I got nowhere. It was so frustrating. You probably know.
This is good, right? I mean, being frustrated is part of our life.
I was very frustrated. You know the cat's proof, right? This is actually my favorite proof, and I believe it's also your favorite proof, because
it's my favorite proof? Huh?
Is it? I don't know.
I don't.
Is it?
No.
No. It's definitely my favorite proof, because it's the only proof I am able to understand right now. But from what I was able to understand from the cat's proof, you have those closed random loops. You have to count in order to get the free energy formula. Mm-hmm. So for the model with magnetized energy component, you can do the same trick, but with loops which you enable to be unclosed. So, so you add also unclosed loops. So that was the idea I was trying to pursue, but I got nowhere. But I'm asking you if, in your career, if you have been trying to solve the same problem, and if there is some vital direction which I should go, or I should forgot this completely, because instead of loops, now you have random paths.
Yes, I do understand. Okay, first we should discuss that later, I guess. But maybe to bounce on this, just the structure of loops in all these loop models that you are referring to is absolutely fundamental. So if you lose the structure of loops and you start to have this path, that life becomes much more complicated. So a priori, this is the kind of things that scare me, but that's also what is cool. So I think it's reasonable to try, but I never did. So I will not be the right person. You have to admit when you don't know. So. I will not be the right person to ask these kind of questions, but we can discuss later. Yes?
Hi. Thank you for the excellent talk. So I have two questions. The first one, what if, I'm assuming that everything done in the context of Ising model, at least in 2D, for example, is that you have a really specific organized kind of grid, like square, hexagonal, and so on. But what if you change this for a random kind of grid? Because I'm assuming that if there's a random, then the way you choose your path for the correlation function maybe gets a little bit complicated, or maybe you don't have the actual way to do this proof. So does it change? This is first. And second?
Well, you will ask your second question after, because I have absolutely zero memory. So if you ask me two questions, I will forget about the second one while answering the first one. So I will answer the second question after, but please. So you have to know yourself. So it's a very interesting question. So you can, for instance, one thing that would be maybe a little bit more regular or more real life would be to have a Poisson point process of points in the plane. So there are things that are basically sampled at random. That's a natural way of sampling at random points. And then you have your spins on this. There you can still do things. You lose integrability, or at least a manageable one, but you can still prove things. But in some sense, it's not very physical, because usually the way the points are going to be sampled does depend on the model itself, the fact that they do interact, for instance, in a ferromagnetic fashion. So imagining that the position is totally random, not basically independent, and then having an Ising model on it would not be naturally what you would see probably in systems. So what is very interesting is to have this kind of double randomness, and joint one, more importantly. So you have, before I had two randomness, position of the points and then easing on it, but in fact there is an interaction between the two. And these models, they become much harder to study, and they are very interesting because then you can ask the question, is a disorder relevant or not in some sense? So the fact that you have a randomness in the position that is joint with the thing, is it impacting the behavior of your system or not? And for instance, for the Ising model, you have maybe a baby question, which is if you think that the edges are now random strength. It's not one, it's not plus minus one, it's plus minus a quantity that is itself random. And there you have some marginal relevance in the 2D Ising model. So these are questions that are very deep. And in particular, I think in 2D, that's probably the last, with the universality question of really managing to do 2D systems, but which are not exactly planar. This question of how you incorporate the randomness of, an additional randomness that is in some sense measuring the impurity in your system, right? Like how far from crystal it is. These are really fantastic questions. People in my group are trying that, and we are trying that. And yeah, it's really cool. They are cool questions.
Okay, great, thank you. For the second one, does it change anything the model or the solution of the model if we allow the, let's say, the particles to oscillate around the fixed point, like in a epsilon kind of oscillation, maybe an harmonic or something? Does it change in anything?
Yeah, so that would be a little bit related indeed to the previous question, but this will probably not change much. What is going to change is if you allow them to have more possible values. And what is very funny is that actually you get very different behavior. If you start to allow the systems to point on a circle, but still on a circle, okay? Then in 2D, there is this very famous BKT phase transition. So you will never have order. So the magnetization will always be zero. It's just that the correlation will be exponential for a whole range of temperatures, the high temperatures. And then it will reach a point where they will become to decay polynomially fast and not exponentially fast. These topological phase transitions, they were by this, discovered by Kostelis, Throughe, and Bures-sur-Yvette. And Kostelis and Throughe, I think, got the Nobel Prize for it in 2018, something like that. What is very funny is that they got the Nobel Prize for discovering these phase transitions. And actually, it's one of the rare cases where mathematicians proved rigorously exactly what the physicists predicted. So Fröhlich and Spencer proved this. And they are absolutely not mentioned in the anywhere in the Nobel Prize thing, even in the description of the work. So it's very funny because you can see that sometimes words that should interact very deeply do not talk to each other, basically. Because I'm sure it's an omission that is not on purpose. So this is what happened. And for instance, if you start to have the most natural model, which is that you are allowed to go in any direction in the sphere. So you are a 2D system, but it's in the sphere. There is an absolutely beautiful conjecture which is still open, which is a kind of baby version of the famous Young-Mills mass gap question, which is that there should always be exponential decay in 2D. And this, if there are probabilists in the room, that's really something I would like to see proved. I'm not smart enough for that, but I'm sure some people are.
Actually, Fröhlich was giving a series of talks in Les Houches in Thales' presence. And Thales was saying, what you are doing there, I already proved it. You know?
Yes.
So, still, question?
Yeah. Why you give the thing, I mentioned another... I thought that, okay. So.
Thank you very much. It was a very nice lecture. I think we are on the Earth. Earth is a rotating body. And it has magnetic poles which are close to the poles of rotation. They move a little bit on the surface of this body. However, what may happen sometimes, that the North Pole changes its position to the South Pole, and the South Pole vice versa to the North Pole. So how to interpret this? Is this a phase transition, or is it...
For us, it will be a big change for sure. But I don't want to be in a plane when this happens. So this is a dynamical systems, right? So here, notice, so it's a system that evolves with time. Here, I was looking at static systems, right? There is no randomness in time. Of course, I can start to make the thing random in time, right? Make the things evolve in time. For instance, by resampling, maybe by perturbing, asking spins at regular times to try to resample. And they will not systematically align with their neighbors. They have a tendency to align, but they could disalign. And when you look at the behavior in time of this thing, even in a system, so let's say it's a finite system, not an infinite one, but a big finite system, even below the critical temperature where things have a tendency to align, if you let the thing evolve sufficiently long, it may switch, go from basically pointing north to basically pointing south. And actually, the weight switch involves very, very interesting mathematics, metastability effect, things like that. So what you are describing would be probably something that at least it rings more this kind of bell to me, which is a system that is basically stable, but still has a few fluctuations. And once in a while, the fluctuation becomes big enough that the system is going to want to reverse. But I don't want to be overextending if this is actually what happened there.
What is the source of magnetism in Earth? It is rotation of the
rotating nucleus of the Earth.
Yeah. So it will not be okay.
Sorry. No, I'm not saying that, Michael. I was making an analogy. No. No, what I meant is that these are systems that are metastable in the sense that they have they are in a fairly stable state. And then, because of the perturbation, the fact that the thing is not purely homogeneous, things like that, it may reach at some point change a barrier break and pass on the other side. And we have this type of behavior in the Ising model. I don't mean that the Ising model is... The Ising model explains basically nothing on magnetism. I lied to you. That's...
All right, thank you for the talk. What about higher order phase transitions? Do they also have this critical scaling phenomena?
So the Ising model is a second order phase transition. And you can look at higher order phase transition. That's your question, right? Like a third order and so on. For instance, percolation, Bernoulli percolation, is having a higher order phase transition in 2D. It also exhibits this universality. You can compute critical exponents, things like that. From that point of view, from our world, I must say that there is not a huge difference between second order and higher order phase transitions. There is a very big difference with first order. It's kind of two different techniques, the discontinuous phase transition and the continuous one. But in the continuous one, it's kind of a spectrum, and you can go from second order to third order. Just to answer, maybe to bounce on your question, the 2D Ising model is exactly borderline second order, exactly borderline. And as soon as you move a little bit, it's third order, but it's fine. That's fine.
Thank you. So you mentioned that in the plane, square grid and triangular grid produces the same critical exponent. So my question is, if you consider other planar graphs, for example, is it known what does this critical behavior depend on? For example, the branching number or some other connectivity properties of the graph?
Yes, so if you take any biperiodic graph, which is strictly planar, okay, so you take your favorite graph, non-degenerate on a torus, finite, and you unfold it to give you a 2D lattice, which is biperiodic. It's not truly periodic, but then you get 1/8. And it's actually essentially proved. I don't know if it's written somewhere, but it's proved. This is really very much in what is done those days. So at least for strictly planar and strictly irregular, like with some kind of translation invariance, it is known. And the reason is that integrability is preserved. It's harder to extract the juice out of this integrability, but it's still integrable.
So it was proved for a three-dimensional case?
Yes.
But can you discover the same formula for any dimensions? And maybe D equal 2 is some specific one?
Very good. So the second half of my talk is the higher, no, I'm kidding. So actually, our result is true for any dimension, larger or equal to 3. So there is no problem with dimension 4 and more. And in fact, 4-dimensional Ising is a very interesting model because this one is much closer to quantum physics, ironically, because it's one model in a family of models which are called the 5-4 model, which are natural discretization for 5-4 field theory, which is in 4D, it's natural because it's 3-dimension space dimension, 1 time dimension. So if you want to cook up a model for a rigorous quantum field theory that would be modeling interaction between 2 particles, for instance, you want to discretize what is called 5-4 interaction. And the Ising model is the right discretization in some sense. And so it's very interesting to work at the 4D and higher dimension a little bit less, but 4D is very interesting. And in fact, it's much simpler than 3D. 3D is the hardest. When you get 4D and higher, I mean simpler with a lot of quotes, but 4D and higher, the models start to have a mean field behavior again, in fact. And in particular, the scaling limit of the model at criticality is what we call Gaussian. And this Gaussianity translates on the quantum side into what we call a trivial quantum field theory, which is, in fact, a non-interacting field theory. So it's very interesting. It's a very good question. It's very interesting to look at 4D and higher. It was the second half of my talk to actually tell you that we have results on 4D in particular and proving triviality in critical. Yeah.
And you have infinite point, so it means that you're starting from infinite system from the beginning, yeah?
Yes, yes, but then, you know, once you understand the infinite system, usually you do get some information on finite systems. Like it's kind of it's the first order approximation in some sense. So you also get information on the 4D system, and like in a box or in a torus, for instance, and you can get what you want. I mean, you describe what you want, basically.
All right, so let me ask you a question. So you mentioned that this Ising model is, can be considered as model of more general cooperative phenomenon. And so let me ask if you know about some, let's say, situation outside of physics. Let's say where phase transitions are studied or even defined.
Or what, sorry?
Whether somehow outside of physics,
so
these phase transitions are studied or even defined.
So one of the difficulties of questions that are outside of physics is that they are usually finite world questions. So for instance, the Ising model is used to model neural networks in our brain, but then the questions that are asked on these systems are much more finite-sized questions. And in fact, even the actual dimension of the graph of interaction, which is materialized in this case by the neurons and the synapses and things like that, these are actually very high-dimensional systems and very inhomogeneous systems. So the questions are a little bit different, and in particular, I don't think that the question of the phase transition itself is the main question there. It's more how you compute interactions. Can they encode, like we go back maybe a little bit to what I was saying on Hopkins, how they encode some information, etc., etc. But I don't know so much.
In markets or in...
You want to make money. I see. This information I keep for myself. No. So same thing, actually, I think for markets. So for markets, there is this question that is very deep, which is that most tools for finance have been cooked up on the premises that the randomness is what we call MIDE. That's Mandelbrot that was using this denomination. So for many, many years, they were thinking that randomness is MIDE. The MIDE randomness is if I want to measure the size, the average size in this room. If I take this group and I measure, I will probably get the size of the whole, the average of the whole group fairly well, because I will have, an average of adult Czech. And this extrapolates, and it's pretty natural, because even if the tallest person in the world enters into this room, it's not going to change the average so much, right? Now, if I do the same question, but I ask something that is going to be related to wide randomness. Meaning, let's say I'm asking the average wealth in this room, not pointing if Elon Musk enters in this room. I do think that our global wealth average is going to change by a lot, right? An individual instance may change drastically the global outcome. And the critical behavior of the Ising model, like the critical behavior of basically any second order, continuous phase transition, is going to make appear things that are typical from the right randomness. And so why did I do this kind of, it's not that I want to keep you as long as possible, but it's because Mandelbrot noticed that in finance, there are actually events that are not ruled by mild randomness, but more by wide randomness, typically financial crisis. And there, to understand these things, it's reasonable to expect that statistical physics, the tools that you develop in statistical physics, could be helpful. For instance, these metastability effects that appear in first-order phase transition, or they could, the clusters. We heard a lot of clusters during the COVID crisis, which was also typically pandemia is typical from wide randomness. It doesn't appear every single day, but when it appears, it totally changes. And we heard about clusters, right, which are typical things that appear in phase transition. So being able to study these kind of things, for instance, in the Ising model at low temperature, it's also something that can give you information on what's the metastable mechanism that lead to a phase transition. In particular, if you start to see clusters of a certain size, they are going to be bigger tomorrow. So, of course, these ones are not big enough to infect the whole population. So apparently, this is a good reason for politicians not to panic. But for statistical physicists, if you start to see the size of the clusters increasing, clearly there is a point where it's going to pass this typical size, and it will become a cluster that will infect everybody. Or I'm not in finance, but in 2008, I'm pretty sure that there were, before the actual crisis, increase of volatility due to certain micro events that clearly were starting to involve more and more things, and that were in fact premises of the crisis that would happen. But I'm not at all specialist of that, and the Ising model is one place, again, a little bit like before, where you see this metastability effect, but there are, in fact, many, many systems that have this, and probably the right system for finance will not be Ising.
Outside of physics, you should mention also mathematics.
I thought that you were still...
What you are doing, I want to call mathematics of physics.
You are a mathematician. The logic is saying that you didn't include math.
For example, they are not motivated by physics.
No, that's true.
And when I first saw random graphs, I was thinking, this is mean field. Why they are somehow studying this stupid system? It is really trivial.
Thank you for this nice conclusion.
Okay. So, thank you.
Thank you very much for your attention.